Welcome to The Explainer. Today we're diving into something that sounds a little bit like science fiction. We're talking about how a layer of material, sometimes thinner than a coat of paint, can make a massive 30-ton armored vehicle practically indestructible. It's a fascinating world where the thinnest layers provide the toughest protection.
So right out the bat, you've got to ask, how is that even possible? Well, it's because modern armor has evolved way beyond just piling on more and more thick steel. We're in a whole new era of super sophisticated, ultra-thin layers. These are coatings so advanced they can literally change the rules of how a material behaves.
And this all stems from a huge challenge that engineers call the armor paradox. On one hand, military vehicles have to stand up to increasingly powerful threats. But you can't just keep adding more steel. That adds a crippling amount of weight. And it gets even more complicated because we're not talking about simple steel boxes anymore. These are complex machines, a mix of steel, aluminum, advanced composites, and even ceramics.
So, if you can't just make it thicker, what do you do? Well, the answer lies in a whole range of incredible high-tech painting techniques. And, forget about anything you'd find at a hardware store. This is material science taken to the absolute extreme.
Okay, let's break down how this stuff is actually applied. First up, you've got methods like HVOF, which is basically supersonic spray painting. You're blasting particles so fast they slam together to form this incredibly dense and tough layer. Then, you've got something even more precise, called chemical vapor deposition. This is wild. It literally grows a new surface, one atom at a time. It's perfect for covering really complex shapes perfectly. And finally, there are laser methods like cladding. The easiest way to think about this is like a 3D printer for metal, where you're essentially laser welding a brand new, stronger material right onto the original surface.
But here's the thing. It's definitely not a one-size-fits-all kind of deal. You can't just slap the same coating on everything. The perfect coat has to be meticulously tailored to whatever it's protecting, whether that's a slab of high-strength steel or a lightweight composite fabric.
And depending on the material, you're solving completely different puzzles. For traditional metals like steel or titanium, the big challenge is pure brute force, withstanding extreme heat and impact. So the solution is often to use super hard alloys or laser-clad ceramics. But for composites, like advanced fabrics, the problem is totally different. How do you get a coating to even stick without damaging or destroying the lightweight material underneath? It requires a whole different playbook.
And one of the most clever solutions, especially for those fabrics, is something called a shear thickening fluid. Seriously, you can just think of it as liquid armor. Most of the time, it's just a fluid. But when it gets hit by a sudden, high-speed impact, well, that's when its properties change in a big way.
So, picture this. A projectile hits a fabric that's been treated with this fluid. Instantly, and I mean instantly, the fluid hardens. It goes from a liquid to a near solid, making that flexible fabric temporarily rigid and unbelievably protective. That sudden hardening spreads the energy of the impact over a much wider area, which is what stops the projectile from getting through.
But, the real magic isn't in any one single layer or technology. It's all about how these different materials and coatings are combined. It's about building a complete integrated system where the whole is much, much stronger than the sum of its parts.
So, modern armor is basically a high-tech sandwich. You start with a strong structural layer, usually steel. Then, you add what's called a breakup layer. This is an incredibly hard ceramic designed to do one thing: shatter an incoming projectile into pieces. Behind that, you have an absorption layer made of composites like Kevlar, which is there to catch all those fragments. And then, the whole thing gets a final functional coating to protect it from everyday wear, tear, and corrosion.
And that multi-layered approach is really the key to solving the armor paradox. It lets designers build protection that can take multiple hits from all kinds of different threats, all while keeping weight and cost in check. And of course, it makes the vehicle last a whole lot longer out in the field.
But as you can probably guess, the innovation is not stopping here, not by a long shot. The next generation of armor is pushing the absolute boundaries of materials science, taking us from the world we can see right down to the nanoscale. Scientists are now engineering with nanomaterials that promise way more than just passive protection. We're talking about things like graphene and carbon nanotubes, which offer incredible strength at a tiny fraction of the weight. And get this, coatings with self-healing properties that can actually repair minor damage all by themselves. One of the most exciting areas of research right now is in a brand new class of materials called high-entropy alloys, or HEAs. Now, think about a classic alloy like steel. It's mostly just one element, iron, with a little bit of other stuff mixed in.
Well, HEAs completely tear up that old recipe. By mixing 5 or more different elements in roughly equal amounts, scientists are creating these totally revolutionary supermaterials. They're tougher, more resilient, and more damage-tolerant than almost any traditional alloy out there today. This is a fundamental shift in how we even think about what makes a material strong.
So, when you look at the whole journey, from that simple paradox of weight versus strength, all the way to these complex nanoscale solutions, it just goes to show you that sometimes the thinnest, most invisible shields are the ones that provide the greatest strength. It really makes you wonder, as this science gets smaller and smarter, what other impossible problems are we going to solve next?